Okay, calculus students, here is a rundown of the notes on the chain rule. Okay, our objective for the day is the student will learn to apply the chain rule of differentiation. The student will demonstrate the ability to apply the new rules of differentiation to provided functions. And your essential question for the day is, do I recognize when or where to apply the new formulas, and do I know how to apply them? Okay, now chain rule is, for lack of a better way of putting it, kind of like an umbrella that kind of covers up a lot of the other differentiation rules that we have. So you'll see that a chain rule can actually apply to just about any differentiation situation that we have run across yet in a single rule. Okay, so let's take a look here. Here's basically what the chain rule says. Now, there are several conditions and structures that are kind of formats that need to be taken care of for the chain rule. First off, we are looking at a function evaluated at a location u. Okay, if f of u is a differentiable function of u, and u can be defined as g of x, okay, which is a differentiable function of x, okay, then f of g of x is a differentiable function of x. So if you're not familiar with this notation, you probably should be. This is a composite function, basically meaning we have one function operating inside of another, and the result of one function is dependent upon the result of the other. In this case, the function f of x is dependent upon what the function g of x is actually doing. Okay, so what we have here is the derivative of y with respect to x is equal to the derivative of y with respect to u, and we'll look at u here more here in just a moment, and that is multiplied by the derivative of u with respect to x. The idea of the function u is to assign u to the innermost part of the composite function and then follow the formula. As I said, we kind of have one function installed into another one. That innermost function is what we're going to call function u. Okay, so let's look at an example of the chain rule in action. Okay, let's find the derivative of y with respect to x for y equals the quantity x squared plus 1 to the third power. Now, this does not fit any known rules that we have thus far, okay, because we have a function embedded inside of another function. So the function x squared plus 1 is inside of these parentheses being cubed. Okay, so what we need to do is we need to kind of identify where the innermost function is, and in this particular case, the innermost function is the x squared plus 1. So we're going to assign that value to be our u. Okay, so basically the derivative of y with respect to x is found by taking the derivative of y with respect to the u function that we just assigned, and then multiplying that by the derivative of the u function with respect to x. Okay, so what we're looking at here is we are going to take the first part of that, the derivative of y with respect to u. We're going to apply our basic power rule to what's going on there. Okay, and then on the last one, that works pretty much exactly the way we've said it was, the sum of those terms. Okay, so the derivative of y with respect to u, that will bring the 3 exponent down and make it a coefficient, and then the dimension of our binomial is reduced by 1 unit down to the second dimension. The derivative at the trail term there, of course, the 2 comes down, reduces down to a 1. The 1 is eliminated, and we're ended up with 2x. And the only thing really to do is to clean up the mess, combine the like terms. Okay, the 2x can definitely combine with the 3, okay, and make 6x. But it's impractical to try to distribute that into the binomial without expanding the binomial. There's just no reason to do that at this point. So we combine our like terms, simplify as much as is easily possible there, and we can leave our answer exactly as it is shown. Okay, the previous question was an example of the general power rule. The general power rule states when a composite function fits the format y equals a function u of x raised to the nth power. Basically, we are treating it as, just like we were before, we're going to bring the n down and then reduce the exponent by 1. But then we're going to multiply by the derivative of that u function with respect to x. Okay, here's another example. Find the derivative of f of x, where f of x equals 3x minus 2x squared to the 4th power. Another example of the power rule. Okay, so the innermost function is 3x minus 2x squared, so that is going to be the function that we assign to u. And I would like you to get in the habit of identifying the function that you are calling u before you get into the problems. Okay, so let's take a look. The derivative of y with respect to x. Okay, we need to apply the power rule to the function u. So we're going to take the derivative of y with respect to u of the quantity 3x minus 2x squared to the 4th power. And we're going to multiply that times the derivative of this function u with respect to the variable x. Okay, well, on dy du, no big deal. The 4 comes down, becomes a coefficient, and the 4 drops down to a power of 3. The derivative of u with respect to x is going to be 3 minus 4x, no big deal. Okay, then we're going to combine our like terms. The binomial 3 minus 4x can combine with the coefficient 4, but cannot distribute into the 3x minus 2x squared binomial because the dimensions on the exponents are not matching. Okay, so we could expand that if we needed to, but again, don't see really any reason to do that. So this would be where we leave our answer. Okay, find all the points on f of x, where f of x is defined as the cube root of x squared minus 1 quantity squared. Okay. So we're going to find the points for that, where the derivative either does not exist or is equal to 0. Okay, well, first things first there, I typically always convert all of my radical notations into exponential notations. Since our derivatives are working numerically, it would be better to see the numbers than the radicals. So I'm going to rewrite it to the quantity x squared minus 1 squared to the 1/3 power. Now, applying law 3 of the laws of exponents, we can combine the two exponents there on the outside, and we have the quantity x squared minus 1 to the 2/3 power. Now, it should be pretty clear to see that you've got your power rule right there, okay, chain rule as well. Okay, so here we go, walking through the steps. The derivative of y with respect to u of x squared minus 1 to the 2/3 power multiplied by the derivative of u with respect to x of x squared minus 1. dy du, we're going to bring the power down and reduce the power by 1 unit, which will take it down to the negative 1/3. And the derivative of u with respect to x would be a 2x. So there's what we're looking at on the next step. Okay, there is some information that we can simplify in there. Okay, dropping the binomial x squared minus 1 into the denominator because of the negative exponent. Now that makes it a positive 1/3 exponent. And then we have 4/3 of an x as well. Okay, now the question is, find all points where the derivative either does not exist or equals 0. So let's look at it one step at a time. Where would this function not exist? Okay, well, examining the denominator, we do not want the denominator to go to 0, so obviously any situation where x squared equals 1 is going to zero out the denominator. Okay, there's two situations that can happen, a positive 1 and a negative 1. Also, what would cause this function to go to 0? Well, the overall value equaling 0 would be the result of the numerator equaling 0, and obviously that would be x equals 0. Okay, find the derivative of x of f of x is equal to x squared times the square root of 1 minus x squared. Okay, simplifying the radical again, changing it into exponential notation. Hopefully what you notice on this step is we have the product rule looking at us, the function x squared times the function 1 minus x squared to the 1/2 power. So we're going to apply the product rule at that particular step. So that means we're going to take one function and multiply it times the derivative of the other, and then we'll take the other function and multiply it by the derivative of the first one. Okay, so expanding into the product rule, we're looking at this, x squared times the derivative of 1 minus x squared to the 1/2, and then adding that to 1 minus x squared to the 1/2 multiplied by the derivative of x squared. Okay, now if you're paying attention to what just happened, the derivative on the lead term over there, that is the chain rule, a function embedded inside of another function. Okay, so expanding this once more into the chain rule. The x squared right there remains unchanged, but the chain rule all across here, we have the derivative of y with respect to u of the function 1 minus x squared to the 1/2. That will be multiplied times the derivative with respect to x of 1 minus x squared. The rest of it remains unchanged. Now going through and actually doing the derivatives as shown, okay, it might be in your best interest to maybe color code some things or use numbers of underlines or something like that as you are getting more familiar with the chain rule. Very easy to get confused on where some of these terms might be coming from. Anyway, the dy du is 1/2 times 1 minus x squared raised to the 1/2 power. Du dx is negative 2x, and ddx is x squared. Okay, cleaning up the mess a little bit, we have some things that can combine over on the left two terms that are multiplying together. We have negative 2x times x squared, and that is negative x cubed. The 2 in the numerator, 2 in the denominator cancel. Okay, over on the right side, we have a 2x kind of hanging on to the back side of the problem. There's really no reason for it to be back there behind that exponent, so we typically move it out front. We have 2x times 1 minus x squared to the 1/2. Okay, now here's where things get a little bit interesting. We got a binomial here, and anytime we have a binomial, we look for things in common that can possibly be factored out. And in that, I see that both the terms have an x that they can forfeit, and both of them have a 1 minus x squared polynomial in them. Now the numerator or the exponents are a little strange, so the question kind of becomes what to factor out. Well, we really don't want a negative exponent to be part of our problem anyway, so it seems like a good idea to probably factor out the negative 1/2 exponent. Okay, now I actually got more information on this slide than I intended to, so let's see what's going on here. Okay, if we factor out an x and factor out the 1 minus x squared to the negative 1/2 power, that takes the polynomial away from the lead term, and we're left with just negative x squared. Now, if you take a negative half exponent away from that, okay, then what we are left with is actually 1 minus x squared to the positive 1 power. And if you are confused or concerned about that, or not really sure why this exponent right there became a negative 1, okay, you can always just reverse the process. And remember, if I redistribute this guy back into this binomial, do I get the original statement back? And the answer would be yes, I would. Negative 1 minus x squared to the negative 1/2 power. When we distribute this in here, this positive 1 exponent that is right there, and the negative 1, they will add together. What's negative 1/2 plus positive 1? It is positive 1/2. So it looks a little strange, but that's the way that guy works. Okay, so a little bit more information can be simplified inside of the brackets. Okay, we can distribute the 2 into the 1 minus x squared binomial now that the exponent is a nice, neat, manageable number. And then we can combine like terms inside of the brackets, which jumped onto the screen before I was ready for it as well. And now you have negative 3x squared plus 2. Okay, the only other thing I see left to do is we have a negative exponent hanging around, and that probably needs to be cleaned up before we leave the problem alone. So let's send that binomial to the denominator. And finally, the simplification is finished. Okay. Now, trigonometric functions also show up in the chain rule, and when that happens, we differentiate them. As you could probably already guess, these are the rules that show up all the way down the right side of your gotta know card, and they follow very much what you already know. The derivative of sine is cosine, but we have to also consider that u is a differentiable function, so it should be differentiated. So we're going to have to take the derivative of u as well. So cosine u times the derivative of u. Derivative of cosine is negative sine, but that also must be multiplied times the derivative of u. The derivative of tangent is secant squared, okay, but the u must be differentiated as well. The derivative of cotangent is negative of cosecant, okay, and the derivative of u. The derivative of secant is secant u tangent u, and then the derivative of u. The derivative of cosecant is negative of cosecant cotangent, and then the derivative of u. Okay, so very similar definitions that you already had. You just need to now take into consideration that u is a differentiable function that we must also tend to before the problem is over. So let's take a look at one. Find the derivative of y if y is cosine of 2x minus 3. Hopefully it's not a big deal to remember or look at the top of the screen and know that the derivative of cosine is negative sine. So in our next step, we are going to have negative sine of 2x minus 3. And then we also need to take the derivative of 2x minus 3. And the derivative, of course, is going to be 2. So dy du of cosine 2x minus 3 times du dx of 2x minus 3. That gives us negative sine of 2x minus 3, and then times 2, and we can move that coefficient out to the front, negative 2 sine 2x minus 3. Okay, your assignment is on page 136, numbers 8, 10, 12, 13, 17, 18, and then 25 through 28.